approach. We then discuss the multimode fiber simulation model, under which we calculate the principal mode, second order group delay matrices, quantization and feedback techniques, and then we discuss the simulation and results. The motivation is to use multimode fiber for multiplexing along different modes to enhance the data rate. One issue in this technique is multiplexing is limited by mode mixing, that is modal dispersion. The solution to those problems are, if it is in linear regime, we use MIMO DSP to compensate for modal dispersion, but the complexity of such system is very high. One alternative is to use feedback principal modes and launch along those. But the issue with principal mode is principal mode work only when the mode mixing depends linearly on the modulation bandwidth. As the modulation bandwidth increases in terms of capital omega square, principal mode suffers from the modal dispersion. We first discuss about the prior work of modal dispersion, and then we discuss about the higher order modal dispersion issues. So the idea of principal mode comes from principal state of polarization in polarization mode dispersion in single mode fiber in 1999. In 2005, principal mode in gradient index multimode fiber has been proposed. This shows that principal mode do not suffer from the modal dispersion and are linear combination of ideal modes, and they can be found out from the fiber propagation operator. In 2005 to 16 duration, principal mode distribution in different fiber coupling regimes and various launching methods for principal modes have been proposed. In 2016, to effectively utilize those principal modes at the transmitter, quantization and feedback of principal modes have been proposed. In 18 further, impact of modulation bandwidth on principal mode was studied, and they have shown that beyond 10 GHz of principal mode degrades its performance for 100 meter multimode and 10 km of few mode fibers. So the same prior work is shown in diagram. In case of ideal mode fiber, fiber transfer function h of omega can be given as u naught. We transmit the signal in the basis of ideal modes. So the ideal modes are A1, A2, and these are the input ideal modes, and the received ideal modes are B1, B2. So the system can be represented as V is equals to h of omega into A. We call it as a zero order system since this is the ideal fiber. But as we go to the practical scenario, h omega depends on the frequency. The fiber channel depends on the frequency. Hence, if we send along ideal mode A1 and ideal mode A2, then the received ideal mode B1 and B2 are the function of omega. Hence, they suffer from modal dispersion. So instead of sending with A1, A2, we send with A principal mode 1, A principal mode 2. Hence, if we fix the A principal mode 1, A principal mode 2, the B principal mode 1 and B principal mode 2 are not a function of frequency. Hence, they do not suffer from the modal dispersion. But as the frequency increases, the term F2 comes with the omega square by 2. So even if we send along the principal modes, at the output side, B is dependent on the frequency. So as we can say, the function B is a function of frequency. B of omega is h of omega into A. So what could be done to reduce reduce the effect of frequency on B? We want B to be fixed or the independent of frequency. So we propose our system with the help of feedback of F2 cap. F2 cap is nothing but the quantized version of F2. Here h of omega, that is the propagation operator, that is u naught in e raised to power j omega f1 e raised to power j omega square by 2 f2. Here f1 is the first group delay operator, first group delay matrix, like first order group delay matrix. F2 is the second order group delay matrix. So if we quantize F2 and feedback with the parameter exponential e minus j omega square by 2 F2 cap, then we can reduce the effect of or cancel the effect of F2. So again we can achieve B independent of the frequency. So the quantization technique uses LBG, that is the Lindy-Buzzo-Gray algorithm, and we feedback F2 along with principal modes. We then compare the frequency response and quantization bit required for such systems. So this is the multimode fiber simulation model shown in this figure. Multimode fiber is divided into k uniform sections. The length of each section is kept small compared to coherence length, within which coupling can be assumed to be small. Each section has a curvature Ki which accounts for bending, twisting, inhomogeneity, and manufacturing defects. Rotation across section is captured by an angle θi to account for spatial mode coupling. Overall multimode fiber is concatenation of these sections. One thing to notice is if the length of fiber is small, it is known to be in the low coupling regime. And if the length of the fiber is large, it is known to be in high coupling regime. So then the overall fiber propagation operator can be given as the concatenation of the uniform sections. So u of omega equals to u of k omega multiplied u of k minus 1 omega and so on up to u of 1 omega, where omega is the angular frequency. Further, the u of omega can be given as exponential e raised to power j theta omega, where theta omega shows the propagation properties of the fiber. Further, u of omega can be splitted into u of omega naught plus capital of omega, where omega naught is the central frequency and capital omega is the modulation bandwidth. So u of omega naught plus capital omega is equals to exponential j theta omega naught plus capital omega. Now we can further split this using the Taylor series expansion. So as you remember, if it is theta omega naught plus capital omega, then this can be expanded as theta of omega naught plus capital omega is equals to theta of omega naught plus capital omega theta dash omega naught plus capital omega square by 2 theta double dash omega naught and so on up to. So if we use those expansion, the equation became u of omega naught plus capital omega is equals to u of omega naught exponential j omega f1 exponential j omega square f2. Now if you want to calculate the f1, that is first order group delay matrix. So f1 can be given as minus j u Hermitian del u by del omega at omega is equals to 0. So eigenvector and eigenvalue of f1 are called the principal modes and their group delays respectively. Similarly, from the above equation, we can find the f2 as well. So the second order group delay matrices is given as minus j in the whole bracket u Hermitian del 2u by del omega square plus f1 square. The derivatives of overall propagation matrix u of omega can be obtained using section-wise derivatives. We use forward differentiation of approximation for each section, and then we use the chain rule to find the overall derivative. So for the quantization, we use Linde-Buzot-Gray vector quantization technique. That is a very famous quantization technique where we find the centroid, split the centroid into two, and according to the number of quantization, we again follow the same procedure. So to build a b-bit quantizer that uses the nearest neighbor quantization, the following condition is enforced. So if suppose Si is the partition, it will consist all those S points that are closer to the Si cap in comparison to the Sj cap, where D is the appropriate distance metric, and it is a very important in the finding the similarity or dissimilarity between the two codebooks or between the two matrices. So second order group delay matrices and principal modes are used to form a training set consisting of several realization of few mode fiber channels for each fiber length. In general, training sets that are divided into SI partition, they are such that if it is related to SI, then all the S components will be closer to the SI cap. So the distance matrix is very important in quantization. Now we discuss about the flag manifold in principal modes that uses the different distance matrices. Since we know that the principal mode are the ideal modes as basis vectors. So each principal mode can be represented as a unit norm vector Pi, where I is from 1 to m. The vector Pi is invariant under multiplication by a unit magnitude complex number. So if you multiply a unit norm vector with respect to e raised to power j5, it will be again the shifted version of the same unit norm vector. So we encountered that for those kind of matrices, the flag manifold distance is the appropriate metric. The advantage is that the number of quantization bit required reduces if we use the flag manifold distance. So this is the flag manifold structure for the 2 raised to power b principal mode codebook. So flag manifold distance is nothing but the diagonal distance. So the distance is given as df of pm1, that is principal mode 1, comma principal mode 2 is given as square root of summation I is from 1 to 1 norm of principal mode 1 ith column into principal mode 1 ith column Hermitian minus principal mode 2 ith column principal mode 2 ith column Hermitians Frobenius norm, and I is iterating from 1 to m. Similarly, for second order group delay codebook, distance metric is given by Frobenius norm between two matrices. Frobenius norm between two matrices is given as square root of trace of difference between the matrices multiplied by difference between the matrices Hermitian. These are the simulation parameter: fiber type, few mode fiber, core diameter 10 micrometer, cladding refractive index 1.444, numerical aperture 0.14, sigma kappa, coupling regime 10 meter inverse, wavelength 1.55 micrometer. So these are the simulation frequency response for 10 km of few mode fiber, we observe that 10-bit quantized F2 along with varied principal mode quantization bit is required to achieve the unquantized performance. So we observe that 8-bit quantized principal mode along with 10-bit F2 quantization is enough to get the unquantized performance. Similarly, for 100 km of few mode fiber, 10-bit quantized F2 along with 10-bit of principal mode is good enough to get the unquantized performance. Also, one thing to notice is that without the feedback of F2, the red curve has the least performance and the black curve with the quantization of F2 has the good performance. Similarly, we calculate the bit error rate for BPSK modulation over AWGN noise in 10 km 6x6 few mode principal multiplexing along with modulation bandwidth is 30 GHz. So we see that with the ideal mode multiplexing, bit error rate is very high, and with the principal mode feedback, bit error rate is reduced up to 10 raised to power minus 2, and with the principal mode and F2 feedback, bit error reduced up to 10 raised to power minus 6. Similarly, for 40 GHz modulation bandwidth, bit error rate for principal mode is up to 10 raised to power minus 1, and bit error rate for principal mode along with F2 feedback is up to 10 raised to power minus 4, which is a very good performance. So we conclude that with very little quantization bit requirement of F2, we can get the principal mode dispersion free nature. These are the references.